The world is drowning in data. Every click, every transaction, every sensor reading contributes to an unprecedented digital deluge. Our current storage solutions are struggling to keep pace, facing limitations in density, longevity, and energy consumption. But what if the answer lies not in silicon, but in the very building blocks of life itself? Scientists are now actively exploring the revolutionary potential of storing the world's data inside strands of DNA. This isn't science fiction, it's the frontier of information technology, offering a paradigm shift for how we preserve humanity's knowledge. We are generating data at an exponential rate, measured in zettabytes and beyond. Traditional storage media, like magnetic tapes and hard disk drives, are reaching their physical limits. They demand vast physical footprints, consume immense amounts of energy, and have finite lifespans, often measured in mere decades. This presents a critical challenge for tech innovators. How do we sustainably archive the ever-growing digital universe for centuries to come? The sheer volume of information threatens to overwhelm our infrastructure. Data centers are energy hogs, and the constant migration of data from aging media is a costly and complex endeavor. We need a solution that is compact, durable, and energy efficient. This urgent need is driving the exploration of radically new storage paradigms, with DNA emerging as a frontrunner. At its core, DNA is a biological information storage system. It's a complex molecule, a double helix, composed of 4 nucleotide bases: adenine, A, guanine, G, cytosine, C, and thymine, T. These 4 letters form the genetic code that dictates all life on Earth. For billions of years, DNA has reliably stored and transmitted vast amounts of biological information across generations. This natural efficiency and stability make DNA an incredibly attractive candidate for digital data storage. Its fundamental structure is inherently designed for information encoding and retrieval. By leveraging nature's own robust system, we can potentially overcome the limitations of conventional electronic storage. The process of using DNA for data storage involves 2 primary steps: encoding digital information into DNA and then decoding it back. This requires sophisticated biochemical and computational techniques. It's a fascinating intersection of biology, chemistry, computer science, and engineering. Encoding begins by translating binary data, the 0s and 1s of computers, into the 4-letter alphabet of DNA, A, T, G, C. Various encoding schemes exist, from simple direct mapping, for example, 00 equals sign A, 01 equals sign T, 10 equals sign G, 11 equals sign C, to more complex methods incorporating error correction codes. These codes are crucial for ensuring data integrity, as DNA synthesis and sequencing are not perfectly error-free. Once the binary data is translated, custom DNA strands are chemically synthesized. This process involves building oligonucleotides, short sequences of DNA, base by base. In June 2019, a landmark achievement demonstrated this capability. Scientists successfully encoded all 16 GB of text from the English Wikipedia into synthetic DNA. This massive undertaking showcased the feasibility of storing large, complex datasets in a biological format. The synthesized DNA is then stored, often in a dehydrated or frozen state, awaiting future retrieval. Retrieving data from DNA involves the reverse process, sequencing the DNA and then computationally translating it back into binary. DNA sequencing technologies read the order of the A, T, G, and C bases in the synthesized strands. Next-generation sequencing, NGS platforms, have dramatically reduced the cost and increased the speed of this process. However, it remains a bottleneck compared to electronic read speeds. After sequencing, sophisticated algorithms are employed to reconstruct the original digital file. This includes error correction, reassembling fragmented sequences, and converting the DNA alphabet back into binary code. The computational overhead for decoding is significant, requiring powerful processing capabilities to manage the vast amounts of raw sequencing data. DNA offers advantages that are simply unattainable with current silicon-based media. Its inherent properties make it an ideal candidate for long-term, high-density data archiving. These benefits are driving intense research and development in the field. The density of DNA storage is truly mind-boggling. A single gram of DNA can theoretically store an astonishing 215 million gigabytes of data. To put this into perspective, all the data currently stored on Earth could potentially fit into a volume no larger than a sugar cube if stored in DNA. This incredible compaction capability could revolutionize data center design, drastically reducing physical footprints and associated infrastructure costs. Further advancements, such as the DNA fountain method developed in 2017, have pushed this density even higher, achieving 215 petabytes per gram of DNA. This level of density is orders of magnitude greater than any existing storage technology. It promises a future where vast archives of information can be stored in incredibly small, manageable quantities. Unlike magnetic tapes that degrade in decades or solid-state drives with limited write cycles, DNA is remarkably stable. Its chemical structure is inherently robust, and it has evolved over billions of years to preserve information. When stored under optimal conditions, such as in a frozen, dehydrated state, DNA can last for an estimated 1.5 million years. This makes it an ideal medium for archival storage, ensuring that critical data remains accessible for millennia. Consider the historical record. Ancient DNA has been successfully extracted and sequenced from fossils tens of thousands of years old. This natural resilience far surpasses the lifespan of any human-made storage medium. For institutions like national archives, libraries, and scientific research facilities, DNA storage offers an unprecedented solution for preserving humanity's collective knowledge for future generations. The field of DNA data storage is rapidly evolving, with significant breakthroughs occurring regularly. These advancements highlight the accelerating pace of research and the growing viability of this technology. Each milestone brings us closer to practical applications. In 2017, the DNA fountain method was a game changer, demonstrating data storage at an incredible density of 215 petabytes per gram. This method uses fountain codes, which are highly efficient for data transmission and robust against data loss. This was a major leap forward in maximizing storage capacity. The year 2018 saw researchers successfully store and retrieve approximately 200 MB of data, a significant increase in practical capacity. More importantly, they proposed a method for random access of data items stored in DNA. This is crucial for practical applications, as it allows specific files to be retrieved without sequencing the entire stored dataset, much like accessing a file on a hard drive. 2019 was a pivotal year. The album Mezzanine by Massive Attack was encoded into synthetic DNA, showcasing the technology's potential for creative and cultural preservation. Also in 2019, a fully automated system was created to encode and decode data in DNA. This automation is vital for scaling the technology beyond laboratory experiments, moving towards industrial-scale applications. Most recently, in 2021, a custom DNA writer was developed, capable of writing data into DNA at a speed of 1 megabit per second. While still slower than electronic write speeds, this represents a significant improvement and demonstrates the potential for increasing throughput. These continuous advancements underscore the rapid progress being made in overcoming the technical hurdles. While DNA data storage holds enormous potential, its practical use is currently limited by several key challenges. These challenges, however, represent significant opportunities for tech innovators to contribute to a revolutionary field. Overcoming these hurdles will unlock the full potential of DNA storage. The primary limitations are the high cost associated with DNA synthesis and sequencing, and the relatively slow read and write speeds compared to electronic storage. Synthesizing custom DNA strands is still an expensive process, and sequencing large amounts of DNA takes time and specialized equipment. These factors currently make DNA storage impractical for everyday active data. For tech innovators, this presents a clear call to action. Developing more cost-effective and faster DNA synthesis technologies is paramount. Innovations in microfluidics, automation, and novel chemical synthesis methods could dramatically reduce costs. Similarly, accelerating DNA sequencing technologies and developing faster, more efficient computational decoding algorithms are critical areas for research and development. Achieving true random access, where specific data files can be retrieved without sequencing the entire DNA archive, is another complex challenge. Current methods are improving, but they still require sophisticated indexing and retrieval strategies. Furthermore, ensuring data integrity through robust error correction codes is essential, as biochemical processes are inherently prone to errors. Innovators can focus on developing advanced indexing systems for DNA archives, perhaps leveraging machine learning for efficient data retrieval. Research into novel error correction codes specifically optimized for DNA's unique error profiles, for example, insertions, deletions, substitutions, is also a vital area. These advancements will make DNA storage more reliable and user-friendly. Integrating DNA storage into existing data center infrastructures and making it scalable for petabyte and exabyte archives is a significant engineering challenge. This includes developing automated systems for DNA handling, storage, and retrieval, as well as creating interfaces that allow seamless interaction with traditional computing systems. The opportunity here lies in designing the next generation of DNA data centers. This involves developing robotic systems for managing DNA libraries, creating specialized environmental controls for long-term storage, and building software layers that abstract the biological complexities from the end user. Scalability solutions, from modular DNA storage units to distributed DNA archives, will be crucial for widespread adoption. It's unlikely that DNA storage will completely replace traditional electronic storage in the near future. Instead, the most probable scenario is a hybrid approach. Active, frequently accessed data will remain on fast electronic media like SSDs. Less frequently accessed, but critical, archival data will migrate to DNA. This tiered storage strategy leverages the strengths of each technology. Imagine a future where the world's most important historical documents, scientific discoveries, and cultural artifacts are preserved in tiny, durable DNA capsules. This cold storage layer would ensure data longevity for millennia, freeing up valuable resources from constant data migration and energy-intensive electronic archives. DNA storage represents a profound shift in our ability to preserve information, offering a sustainable solution for the digital age. The journey to unlock DNA's full potential as a data storage medium is just beginning. This field is ripe with opportunities for innovation, demanding expertise from diverse disciplines: molecular biology, chemistry, computer science, electrical engineering, and materials science. Are you ready to contribute to a technology that could redefine how humanity stores its knowledge for millennia? Dive into the research, explore the challenges, and envision the solutions. Share your insights, collaborate with leading scientists, and help build the future of data storage. Your expertise could be the key to transforming this groundbreaking science into a practical reality. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.